Thank you to boot.dev for supporting PBS. Some people worried that the Large Hadron Collider would smash particles together so hard it would make black holes that would swallow the Earth, open wormholes to other dimensions, etc. It didn't, and it won't, but the LHC may be making a very different kind of portal. A portal to the dark sector. This isn't another name for the Upside Down. Rather, it's a hypothetical family of elementary particles that exists in parallel to the familiar particles of the Standard Model, but are invisible to the Standard Model, invisible to us, and therefore could be the answer to the dark matter conundrum. And what is this portal? Well, it's the particle that the LHC was built to find in the first place, the Higgs boson. We've got a couple of quick announcements before we start. First, our eternal battle against the algorithm continues. The best way to encourage YouTube to share our videos is to like and comment. Doing both really makes a difference. And if you're new here, subscribe, hit the bell, and introduce yourself in the comments. We're friendly. Next up, we're excited to launch our Composition of the Universe nickel and enamel pin, now with a holofoil backing. If you want to flex your knowledge of dark energy, dark matter, and the terrifyingly small slice of ordinary matter that you and our world is made of, check out our first pin of 2026. And if you prefer your mornings fueled by dark energy, we've also got a brand new dark energy mug. Plus, our UV glow Kerr rotating black hole hoodies and shirts are still available. Links in the description. Now, onto the episode. The Higgs boson was discovered with the Large Hadron Collider back in 2012. Physicists celebrated, a few collected their Nobel Prize, and they got back to work. They amped up the collider with the expectation of discovering the particles that would lead us to the next level of physics. For example, supersymmetric particles that would simultaneously explain the Higgs mass, give us candidates for a dark matter particle, and even bolster string theory. No such particles appeared. Okay, so maybe the undiscovered particles are just so massive that there wasn't enough energy yet to grant them that mass. E equals mc squared, so not enough E for the needed m. So we kept juicing up the collider and kept finding nothing. At this point, the LHC is near its maximum planned energy, 6.8 tera electron volts in the most recent run, and the design goal is 7 TeV, so it's unlikely that new particles will appear before it maxes out. Disappointing? Maybe. But was it worth building the LHC just to produce the Higgs? Absolutely. Besides completing the Standard Model, it could well be that the Higgs boson itself is the key to the physics that lies beyond, and that physics may finally explain dark matter. Now, searchers for dark matter have typically focused on finding a dark matter particle, as though a single add-on to the Standard Model could solve the problem. One of the best such candidates was the sterile neutrino, which Fermilab recently put to bed as the simplest way out of the problem, as we recently discussed. Now, this might still work, but it's getting dodgy. Or it could be that one of those undiscovered high-mass particles, like those predicted by supersymmetry, are dark matter, but again, the LHC almost certainly won't find those. In general, the parameter space for dark matter as a single particle is getting worryingly narrow. But, just maybe, the problem is that dark matter isn't just a single particle. Maybe there's an entire family of particles that exists in parallel to the Standard Model that are all invisible to us, and by us I mean us Standard Model creatures. How would that even work? In order to do the job of dark matter, the candidate particle needs to be very difficult or impossible to detect via interactions with the Standard Model forces, electromagnetism and the weak and strong nuclear forces. Their coupling to these forces needs to be weak or non-existent, leaving only gravity as the force linking those dark particles to the Standard Model. In order to be invisible to the Standard Model, dark matter cannot possess any of the Standard Model charges, so no electric charge, no color charge, no weak charge. We can imagine single particles like this, but we can also imagine an entire family of particles with no coupling to the Standard Model. Such a family is called a dark sector, and its stable particles would be good dark matter candidates. Now, just because a dark sector doesn't hold Standard Model charges, it may still have its own charges and its own internal interactions. It could even look a lot like the Standard Model. So maybe we'd have dark quarks, dark leptons, dark bosons that could interact to give dark protons, even dark atoms. Or its interactions might be very different to the Standard Model. Based on how dark matter appears to be distributed in our universe, our hypothetical dark sector probably isn't forming the same cool structures as the Standard Model matter. So there probably aren't any dark sector planets or dark sector aliens in the room with you right now. Probably. So what's the use of a dark sector? Well, its particles could be light enough to already be within the energy range of the LHC. Because they're dark, the LHC detectors won't spot them directly, but that doesn't mean we can't notice their influence. Let's look at what happens then when two protons collide in the LHC. You can think of protons as tight bundles of several quantum fields, like knots in which each thread has its own internal weave. Collisions momentarily loosen these knots. They can then retie themselves in different forms. But not just any forms. Parts of the knot are undone or retied only in pairs. And the weave of the threads, the symmetries of the fields, persist in the retying, in the final particles. That means that conservation laws must be obeyed, energy and momentum and various charges. And also, internal symmetries must be respected. A dark sector's symmetries can look like those of the Standard Model, but they come from different gauge fields, different weaves to its threads. And that results in different types of charge that don't talk to the forces of the Standard Model. So obliterated protons don't produce the fabric needed to make such particles. Not directly, anyway, but there is a way. If some of the debris of the proton collision can settle down into the simplest possible field configuration in the Standard Model, one lacking the complex symmetries, then that particle could then go on to decay into dark sector particles. Now, the least knotted part of the quantum field weave can be retied into anything respecting its simpler symmetries. More technically, only uncharged Standard Model field configurations, so-called singlets, can couple to the dark sector quantum fields. We call these dark sector portals, and these field configurations are the only way to move energy between the Standard Model and the dark sector. There are very few such portals. Examples include photon-dark photon mixing, the hypothetical sterile neutrino and axion couplings, and the Higgs field interactions. The Higgs may be the most promising of this group. Knowing that the Higgs exists and knowing how to make it is certainly important, but the Higgs is arguably the cleanest dark sector portal. The Higgs field is a scalar field, the simplest possible quantum field. Besides being less knotted by complicated symmetries, scalar fields are also uniquely good at coupling with other fields. That's why the Higgs couples so widely to grant particles their masses. So the expectation is that the Higgs would also be great at coupling with other sectors, including dark ones. Okay, great. Big takeaway. The Higgs boson can transform into dark sector particles. I'll come back to how we actually detect these, but this is already exciting. Because although the LHC hasn't produced lots of new particle types, it can definitely make Higgs bosons. So then what's it going to take to peer through this Higgs portal into the dark sector? The first is to help the LHC do what it does best, but even better, to produce more Higgs bosons by increasing what we call the beam luminosity. That's just the number of collisions per second, which is very different to the amount of energy per collision. The collider is currently switched off and in upgrade mode. When it turns on again in 2030, the new high luminosity LHC will produce a factor of 10 more collisions per second, and over the following decade or so is expected to produce around 380 million Higgs bosons, 10 times more than all previous datasets. Producing a ridiculous number of Higgs bosons is a start, but it's not going to be enough to find dark matter. We also need to make another change. We need to stop throwing away all of the interesting data. In fact, we have probably already trashed a ton of evidence for the dark sector if it exists. But don't judge, we kinda had to. When you collide protons at 99.999999% the speed of light, a lot of stuff comes out. For the most part, combinations of the well-known standard model particles without even a Higgs in the mix. And with roughly 600 billion collisions per second, the many layered rings of detectors around that collision point are just strobing with activity, and it's mostly boring activity. Finding signs of interesting physics, like the decay of a Higgs boson, is like looking for a needle in a haystack. And that's actually possible to do, given enough time. But we don't have time. Assuming a modest 1 megabyte per collision, that means around a petabyte of data per second. It's impossible to store it all for later inspection. We need a way to quickly sort the data, discard the noise, and save the interesting stuff. So leaning into the needle in a haystack metaphor is like trying to find a single needle in every, 1,000 haystacks. When you have a haystack being thrown at your face every second, you can't collect all the haystacks. Instead, you have a split second to decide whether to just duck or keep that haystack for later. And the ones you duck are gone forever. So, LHC experiments achieve this haystack sorting with what's called a trigger. A given burst of detector flashes is correlated with each other in ways that may match interesting physics, like the particles that you get from a Higgs boson decay. Those data are then kept and everything else is thrown away. And all of this is done in a split second. But there's an unavoidable issue. How do you really know that you've encoded all the possible interesting physics into the way we set up those triggers? What if we set them all to catch the needles, but the haystacks also had diamonds? Okay, enough with the metaphors. Let's look at a concrete example of detecting a Higgs boson with LHC detectors. These detectors are constructed in layers. People like to say they're like an onion, but they're more cylindrical, so a leak? Details matter. Each layer is optimized for gathering energy from different particles. The innermost layer detects how charged particles bend in a magnetic field. Then we have the electromagnetic calorimeter, which absorbs energy from electromagnetic interactions with particles like electrons and photons. Then the hadronic calorimeter, which catches anything built out of quarks and gluons. And finally, the outermost layer is a muon detector. Now, experimentally, muons are particularly clean and easy to identify at colliders. Their trajectories to the point of detection can be reconstructed, as can the mass and momentum of the particle that produced them. Combined with our triggers, this lets us really fine-tune our experiment to look for Higgs decays. And that's because the Higgs boson is so unstable that it doesn't move far from its creation point before falling apart. If we can reconstruct the trajectories of decay products, as we can with muons, we can find that they trace back to the proton collision location. And this sort of trajectory origin for decay particles is actually a standard cut that LHC experiments make in order to reduce the amount of data that needs to be sorted. Okay, now, let's actually add the dark sector to this picture. There are lots of ways to imagine a dark sector, but for the sake of this, let's just say that it arises from some sort of parallel standard model with dark quarks, dark leptons, dark photons, etc. All of these interact via non-standard model charges and so are invisible except via a few portals like the Higgs. If this sector actually exists, then some Higgs bosons created in the LHC should decay into dark sector particles. For example, they could decay into a dark quark, dark antiquark, or is it dark quark, anti-dark quark? Anyway, those quarks will then do the same thing as regular standard model quarks. They'll become hadrons and mesons within the dark sector, like dark protons, dark pions, etc. Some of these will be stable and they'll go off and join the rest of the dark matter in the universe. But other dark sector particles will be unstable and they could decay back into standard model particles via another dark portal. For example, they could decay into dark photons, which can then become regular photons and then finally turn into something like a muon-antimuon pair. Now, that sounds like a complicated scenario, and it is, but the complication is really the need for a portal both into and out of the dark sector. Besides that, this is just the standard stuff that happens after a particle collision, leading to detectable particles that indicate the Higgs as an origin. In our two examples of Higgs decay, we ended up with muons. In the first case, where the Higgs decays directly into the muons, the trajectories of the latter could be traced back to the proton collision point. In the second case, where an intermediate dark sector particle was produced, it's like the decay chain took a little sojourn through the upside down before popping back into the world. And that means the final muon will have trajectories that trace back to somewhere that's displaced from the proton collision point. Maybe you can see the problem here. If we are throwing away detections based on trajectory origin, then we're throwing away all of these cases with a dark sector intermediary. That sounds like bad news, but the good news is that it's conceptually straightforward to fix this. When the high luminosity LHC comes online in 2030, it'll do so with an update to the trigger algorithm. To start with, this would mean incorporating muons with displaced origins into the data scouting algorithm. Now, data scouting means recording minimal detail about events to build up a case for storing more detailed data. In the case of the displaced muons, if there appear to be a strong signal of these guys, we'll go ahead and record more detailed information for those muons originating off the collision point. Depending on the unknown properties of the hypothetical dark sector, significant evidence of displaced muons could come within a year of the high luminosity LHC switching back on. But it could also take several years if, say, the coupling is weak or the decay rates are inconvenient. Even then, more work has to be done to build up the argument that these displacements are due to dark sector intermediaries. Things like the mass distribution of the intermediary particles, their decay timescales, and various other things need to match plausible models. But if all of this comes together, we'll have a front-runner solution for the problem of dark matter, one of the most persistent conundrums in all of physics. And all we had to do was exactly what we were doing, just a bit smarter, watching the Higgs bosons pop, but now echoed through the dark sector and displaced through space-time. Thank you to Boot.dev for supporting PBS. Boot.dev knows that learning programming is challenging, but they believe you can learn to code by doing what you'll actually do at a job, building real projects. Boot.dev uses tactics from modern game design to help students build in Python, SQL, and Go. On Boot.dev, you'll be trained by a personal AI tutor named Boots, a wizard bear, who will guide you as you earn XP, unlock achievements, complete quests, and fight bosses that help you learn to code. You can use the training grounds, where you can grind infinite challenges before you forge ahead in your coursework. You'll also get access to the Boot.dev community, which has tons of real humans to help you if you ever get stuck. So, if you've ever wanted to learn to code, Boot.dev is here. Go to Boot.dev and use the code SPACETIME to get 25% off your entire first year on the annual plan.